Good afternoon. Today we start part 3 in machine learning, where we review some concepts of probability and Bayesian theorem, and also we will discuss some probabilistic models and the connection between the probability and machine learning. In the second half of today's lecture, we will have a quiz. It will be done over model. So it will be, we will inform you the time where the quiz becomes active in your model. So you can do it with your computer or your mobile phone. So it is MCQ, so you just selection of the proper answer. Okay. What is the connection between probability theory and machine learning? Why we should study probability? Actually, machine learning, that we know that they are algorithms that can be used for regression, classification, or clustering. It means that we are looking for building algorithms that they can model data that we have. But actually, we have also some serious uncertainties about the model itself. What is the kind of model that fit the data? So we have uncertainty about the model. We have uncertainty about the data. We have uncertainty about if there is missing of information from data. So sometimes we know that we missed some data, but also sometimes that there is missing data, but we don't know about them already. And noise, biasing in the data, or noise, corruptions, disturbance, all these things are uncertainties. So we have a lot of uncertainties about the model, about data, about noise, about disturbance, about missing of some of information, or part of the information is incomplete. So all these things formulate some kind of uncertainty, and a probability theory is the major tool to deal with uncertainties. So probability theory is the math that gives us the ability to quantify uncertainty. So understanding probability is essential for deep understanding of machine learning algorithms. Okay. Indeed, that you don't need to know probability theory in order to be able to write simulation codes. So you can write software or code without any background in probability theory, because actually coding is very deterministic. And also, you don't need to know probability theories in order to run some machine learning ready codes over available data. So if you have ready codes or ready machine learning packages and you have data, maybe you don't need to know anything about probability theory in order just to run or to classify or to cluster some data available with you. However, you will not be able to understand the essential concepts of machine learning and also their origins without probability. Without being familiar with probability theory, we will not be able to develop or even improve the current machine learning algorithms to fit the characteristics of your data. Okay, now, for example, you want to cluster some data. There are many available packages to do that. But behind every algorithm, there is some assumptions. Okay, for example, one of very famous assumptions that data are distributed according to multivariate Gaussian. So we assume that the data is multivariate Gaussian. In that sense, there are many algorithms already derived, and also there are some packages that they can do this, but for what? For multivariate Gaussian. If your data is not following to be multivariate Gaussian or normal distribution, it might follow some like gamma function or some gamma plus exponential distribution or some special kind of distribution of your data. If you don't have a proper background in probability theory and stochastic process, first you will not be able to see what is the what kind of distribution your data have, and the second thing, even if someone told you about the distribution, you will not be able to derive like a special algorithm to work with your data. You will be able only to use the ready-made packages, the ready-made algorithms, and those algorithms usually they are very general, so they are applied for with some general assumptions. So you will not be able to develop or even improve any algorithm without being familiar with some concepts of probability theory. Actually, machine learning does not make the proper sense without probability theory. So without probability theory, the machine learning algorithms, they don't make the proper sense for to understand what is behind it, because machine learning is to resolve uncertainties, and uncertainties can be quantified based on probability theory. So probability theory is the math that we can use to quantify uncertainties. Just to give an example, if you have like some data, let's say 1, 2, 3, okay? This data can be generated from any process. So, but we don't know the process. We don't know the process itself. What is the kind of process? So, how could you predict what will be next? It is very difficult to predict what is next, because just 1, 2, 3 can be anything. It can be generated from anything. So what is next can be, for example, -4. It can be 100. Can be 0. Can be anything. So if I asked you to guess what is next, so you will just say any number. Okay. If we give this for our machine learning and we want to learn the process which generate 1, 2, 3. One possible approach that, of course, the process itself here, we don't know it. But we have big uncertainty about the process. But we can put some assumption. So if we assume that this process, the generated numbers, following, for example, normal distribution, as we will explain today what is the meaning of normal distribution. So we know the distribution of the numbers generated from here. But this number 1, 2, 3 can be generated from any kind of normal distribution, because every normal distribution is characterized by its mean and its variance. But any normal distribution with any mean and any variance can generate these numbers. Okay, what is the best distribution that generates this number? So it is called maximum likelihood. Now we come again for probability theory. What is the meaning of maximum likelihood? In order to find the mean and the variance of this process. Once we build some algorithm or some like assumptions, based on the assumptions that we build or we resolve the uncertainty, then we can guess what is next with certain probability. So I can say that what is next can be, for example, greater than 0 with that probability, or less than 0 with that probability. So now I start, instead of being completely confused, I can give any number. Now I can be more sure, a little bit sure, that the number will be that with that certainty factor. Okay. But someone else can maybe he told you that the distribution of this process is not normal distribution anymore, but it is, let's say, exponential distribution. Okay, and that generates these numbers. But you don't know what is the kind of exponential parameters. Then how to use the numbers to find the parameters of that distribution based on some maximum likelihood criteria. So this is very simple example, that we need to study the probability theory, the models, the probability models, in order to be able to build high sophisticated machine learning algorithms, and also to understand the current machine learning algorithms. So studying probability theory and the stochastic process is a crucial thing in machine learning. However, probability theory, as you know, that it can be like given in several courses, not even one course. And we try to cover this topic within like 2 lectures. So we will just concentrate on the major things here, some basic things, some major things, and also but sometimes we skip some slides here. However, the slides are intensive in order that if you like to read more, so you have the material on the slides. Who studied probability theory before? So just raise your hand. Okay, quite many. But still, even if you studied, but we will revise it again for the purpose of this course. Okay. Concepts of probability. So as I said, probability theory provides a quantified measure for the uncertainty of any process. So if you have some uncertainty, so you are not certain what will be next, then we will need the probability theory as the math to describe or quantifying the uncertainty. So in real life, we cannot be 100% certain about almost anything. I mean, even if we have measurement, but we have also some probability of error or noise in our measurements. So always what we observe, it has also some percentage of errors. So to be 100% sure, this is not possible actually, unless we have some strict assumptions. If we put some strict assumptions that within that assumption we can be sure, but in general, for physical behaviors, we are not like 100% sure about many physical aspects. We have 2 kinds of uncertainties, that like random by nature. Okay, so the process itself cannot be modeled deterministically, even whatever you have information about it. So it is like thermal noise, or like in quantum mechanics. So we know that there are some behaviors that they are random by itself. So it doesn't matter how much information that you have about it, you cannot model it, or you cannot predict it 100% sure, being 100% sure. Then the second kind of uncertainties is uncertainties because of lack of information. For example, we don't know the exact model. If we have this resistor R, and then we have current I, then we can build the relation between Ohm's law, between the resistance and current, that the voltage across this resistor is equal to R times I. But this is accepted under very strict assumptions, that the temperature does not change, the resistance is not function in the temperature, or at least it is fixed. So there is no humidity, and it is DC, because if we have like alternating current, if we have like frequency, so the resistance will be affected according to the skin effect. And also, for example, we assume that it is noise free, because there is noise actually here, so it should be some noise with every resistor. So we put a lot of assumptions in order to say that this model. But in reality, that the model is V equal to Ri, but R is functioned in the temperature, in aging, so at what time, in humidity, and many other factors, and also multiplied by the current I, which is also functioned in the frequency. So if there's frequencies or it is not DC, then this will affect the voltage. And finally, we need to put also some modeling error here. Some modeling error. So here we have the current, and plus the modeling error. So always we have some uncertainty. So this modeling error represents our uncertainty about the process. Okay. Now, if we like to quantify or to put some basis of the math that describes this uncertainty, we will start with, for example, the experiment of tossing a coin. So if you have a coin, this is the simplest example that we use to express probability theory, because if you have experiment that generates only one output, then it is deterministic. So we know always that it will generate this output. But the minimum number of events that we need in order to define uncertainty is 2 events. So if you have from this experiment, you might get event E1 or event E2. So it has only 2 events. This is the simplest, like, random experiment that we can describe, because you have uncertainty which event will appear. Which event will appear. So if you toss or throw the coin, then you have head or tail. So this is the simplest way that we can have. So here you might have event 1, which is, for example, head, and event 2, which is like the coin landed tail. Now we have uncertainty. How to resolve this uncertainty? Is it possible to be sure 100% if I throw the coin to know is it tail or head? Theoretically, yes. Theoretically, yes. Because when you throw the coin, then it will be head or tail, depends on many factors. For example, the initial phase, how it was initially on your finger, for example, let's say initial condition I, okay, and maybe also the force of tossing, so maybe F. So your height over the land, that will or the height of the tossing, maybe H. So the material and the weight of the coin, okay, and the how solid of the land, for example, and many parameters. So if you know all parameters regarding to this tossing of the coin, and also you was able to build the function, then you can be sure that if it is now it will be head or it will be tail. But actually, even for this primitive example, I can say it is very difficult to find all this, like to have this function with 100% accuracy. It is extremely difficult, because you cannot even be 100% sure about the force and the height and everything. Because for the height, for example, your height, you will measure with this with the distance, but this distance cannot be 100% accurate. It can be 99.999, but cannot be 100%. So actually, we have some error in every parameters. So to get 100% sure, it is very difficult. Even actually with this one, this experiment, even be sure like 95% is not easy to find. Even, and this is very primitive, like and simple experiment. Okay, but if you don't know anything about this information, how to say, is it to the landed coin will be head or tail? Then, if we are completely uncertain, then we say 50%. So it is 50% to be head and 50% to be tail. This is what we can do. So it is half and half. Why? Because we have maximum uncertainty. Maximum uncertainty. If you know the guy who throw the coin, so he do it with certain trick, okay, that to get 70% to be head, for example, 70% to be head, we know by default that directly that it will be 30% to be tail, because we have only 2 outcomes, either head or tail. So now, if it is 70% to be head, we can say that our uncertainty becomes less. So the worst case is to be 50-50. in case of two events, the worst case to be 50-50. If you are like a decision maker in some company, and now all information in front of you, it gives you that to take this project or not, the risk, you don't know like about the risk, so it is 50-50. So what decision that you should take? It is like you take the coin and just throw the coin, because you are 50-50. You don't have any like proper information helps you to take the right decision. Because if you know that the risk is 55%, of course you shouldn't take that decision. But if you are 50-50, then you cannot to take any proper decision based on that. So just you throw the coin. Like today in the quiz, in the MCQ, if you don't know the answer, then you just shut your eyes and select one of them, because you cannot make any decision based on that. Okay. Let us start with another example, that if you throw 3 coins, not 1 coin, we know now if it is 1 coin, we have 2 events, okay? But if we throw 2 coins or 3 coins, how many events that we have? 8. 8, because we will have like either all 3 coins will be landed heads, so it is head, 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 or the first 2 coins landed head and the third coin landed tail, or the first coin landed head and the second tail and the third head, and so on. So, and the final one is tail, tail, tail. So we have 8 outcomes of throwing 3 coins. So in that experiment, this experiment, we can have like event E1, event E2, until event E8. So we have 8 outcomes from head, 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 until tail, tail, tail. Now these events, we call them like mutually exclusive. What it means? It means that if one of them happen, the others cannot happen at the same time. So if you throw 3 coins together and you get head, 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 it will never, and it is impossible to be in the same time tail, 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 because that's happened. It is head, head, head. So the appearing of one event will make the others possibility zeros. Okay, so now when we get one of them, the others become 0. This is called mutually exclusive, as we will see later. Okay, and also you can define new events. For example, if you define the event that the second coin landed head, if this is the event that you want the event, or define the event that the second coin landed head, for example. In that case, this event can be represented like, for example, head, 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 or, for example, tail, head, tail, or, for example, head, head, tail, also because the second is head, or tail, head, head, yes. So in that case, you will have 4 outcomes. You have 4 outcomes. So this is the definition of head, of events and the outcomes. The question now, if you throw these 3 coins, you know that one of them must happen, because you take the experiment, you throw 3 coins, maybe together or one after one, and now one of these outcomes will happen. So what it means, first, the set of all possible outcomes, we call them sample space. So the set of all possible outcomes, we call them sample space. So the sample space of this experiment will be like from head, 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 until tail, tail, tail. So we have all of them. What is the probability of S? What is the probability that if you throw 3 coins, you will get head, 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 or head, head, tail, or tail, head, head? I mean any of them. What is the probability that you get any of them? Of course, the probability is 1, because one of them must happen. One of them must happen. because now this is the probability of the sample space. Sample space is the set contains all possible outcomes from certain experiment. So the probability that any of those possible outcomes to be happen, then the probability is 1. So because one of them must happen. Of course, it is not possible that you throw 3 coins and then you get, for example, like 10 euros paper. It is not possible unless you are magic. But in this case, one of them must happen, that you throw 3 coins and then you get either from head, head, head until tail, tail, tail. One of them is the probability is 1. Okay. Now, if we assume that any outcome is the chance or the uncertainty or the chance of any outcomes to appear, they are the same. They are the same. So now we have S. We said in S we have head, 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 tail, head, tail, head, then head, tail, tail, then tail, head, head, and then tail, head, tail, and tail, tail, head, and tail, tail, tail. So those are all 8 outcomes. So if the chance of every one is the same, we call this experiment as equally likely. Equally likely because the chance for every outcome to appear is the same. Okay, now we know that probability of S is equal to 1. As we will see that the probability, if you have multiple events and they are mutually exclusive, so the probability that of multiple of them, it will be the summation of their probability. So this will be the probability of head, 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 plus probability of head, head, tail, plus and so on, until probability of tail, tail, tail. This is always true when they are mutually exclusive. When there is no, the intersection between them is 0. So the probability of any of them will prevent the others from being appear. In that case, if the summation is equal to 1, if the summation of this equal to 1, then, and they are equally likely, they set the same, and their number are 8, then the probability of each one will be 1 over 8. Because we have 8 outcomes, and the summation of them is equal to 1, then the probability of each one is equal to 1 over 8. This is one possibility that we build or we have quantification of our uncertainty for each one. Okay. There is another way that we can find, because it is not always possible that to know the experiment in this simple way. So sometimes we have observations, but we don't have all the all possible outcomes which formulate the experiment. So we can observe. So every time we observe the experiment, we see that how many times the events happen. So we have certain experiment. Okay, so it was not that easy like in this coins example. So we have certain experiment, and we are looking for certain event to be outcome from this experiment. So every time the experiment increases, for example, it is the number of trials of this experiment is n, and then we count how many times the event that we are interested in, E, how many times happen. So we call it like NE. For example, if the experiment repeated, let's say 100 times, this is N equal to 100, and NE, the number of events that we are interested in, happen 20 times out of 100, then one definition of the probability that it will be 20 divided by 100. The error here will be high. The error can be reduced, or our certainty about this experiment, about this number of the probability, will be increased as the number of experiments increased. For example, if n becomes like 10,000 times, and in that case the number of events happen, let's say it was 222, for example, or 2000 200, then we are more in general, of course, in general, we are more confident about this result, that 2,200 divided by 10,000. We are more confident about this result than this result. As the number n increases, as we are more confident about the result. So in general, as a definition, the probability of event E to happen is the limit when the number of trials or repetition of the experiment goes to infinity, and then we find how many times event E occurred divided by the total number of trials itself. So this is the way. If this number, of course, if we have experiment, repeated it 1,000 times, and every time it gives the same event, then we say that the probability of this event will be very close to B1. So we are certain that every time we repeat the experiment, we will have the same output. But if the experiment that we are, or the event we are interested, happens like it didn't happen at all within 1,000 times, okay? Of course, we can say that it is 0, but sometimes it is not 0, but the probability is less than 0.001. For example, the probability can be, for example, 10 to the power minus 6, so it is very rare to happen. So 1,000 times was not enough to see the outcomes of the event. Those are some general rules in probability. So we have 3 axioms in the probability theory. They say that the probability of any event A is always greater than or equal to 0. So the probability cannot be negative. Okay. The probability of omega, or for the sample, omega here is the sample space. Okay. So the probability of all sample space is equal to 1. And if A and B are disjoint events, then the probability of A or B is the probability of A plus probability of B. So those are the main 3 axioms where all probability theory is built over them. And based on this, we can also prove some important theorems, that probability of the sample space minus event A is equal to 1 minus probability of A. Probability of phi equal to 0. If you throw 3 coins, what is the probability that you will get nothing? Is 0, because you should get something, like head or whatever. But the probability that you get nothing is 0. And in general, the probability of A or B equal to the probability of A plus probability of B minus probability of A and B. And this can be seen easily. For example, if we have sample space S, and then we have certain event, and here we have certain event. So we have event A and we have event B, and here is the intersection between A and B. So it is A and B. This is called A and B. This is the area between them. Okay. So the probability of A or B is equal to probability of A, this one, plus probability of B, this one. But you can see that the intersected area is repeated 2 times. First with A, and second with B. So this area should be removed. So then we say minus probability of A and B, because this area repeated 2 times. 1 time with A and 1 time with B. So we removed one of them. This is the reason that we have this. And the probability of A and B is less than or equal to probability of A or B. This is always, and this will be always less than or equal to probability of A plus probability of B. And if A is subset of B, then probability of B minus A equal to probability of B minus probability of A, and so on. So there are some Venn diagrams here to explain those concepts. Okay. Now if we take another example, that we throw a die. So a die has is the cube which has dots, and then we have 6 dots on the cube. So this is the experiment. So the sample space is either 1 dot or 2 dots until 6 dots. Okay. So if I ask you what is the event that when you throw a die, then you will get even number. So then this event is 2 and 4 and 6. Okay. If you have 2 dice you throw them, then of course we have either 1, 1, means that the first die gives 1 and the second die gives also 1, so 1 dot and 1 dot, and 1 and 2 until we have 6 and 6. So this is the sample space. We have 36 outcomes that we can formulate out of this experiment. Okay, so if you play a game that throwing 2 dice and you win if the summation of the numbers of the dots is a prime number, what is the probability that you will win? Okay, again, if it is equally likely means that the chance for every outcome will be the same. So now if you throw 2 dice, as we said, you have from 1, 1 until 6 and 6. So we have actually 36 outcomes. We have 36 outcomes. So we can put them in this way. So S equal to, for example, like 1 and 1, 1 and 2, and so on until 1 and 6. Then you have 2 and 1, and you continue until 6 and 6. So you have 36 outcomes. And we know that the probability of the sample space equal to 1, and because they are disjoint events, because any one happen will prevent the others from being happen. So since, in that case, we will have, this will be one probability of the event 1 and 1 is equal to the probability of event 1 and 2. Every one will be the same as 1 over 36 because there are 36 events, they are equally likely, and the summation must be 1, then every one should be 1 over 36. Okay. Now the question, or you will win if the summation is prime number. So the events E, in that case, we count how many prime numbers we can obtain. So 1 and 2, the summation is 3, so it will be prime number. 1 and 3, no. 1 and 4, yes, because the summation will be 5. 1 and 6, yes. 1 and 4 is 5. 1 and 5 is no, because it is 6. 1 and 7. Okay. So we, sorry, 1 and 6, sorry. 1 and 6. And then we have 2 and 1, 2 and 3, and 2 and 4, no. 2 and 5. And 2 and 6, of course, no. And then 3 and 2, and so on. So in that case, you count all the events or the outcomes where the summation is a prime number. Then we will have 14 outcomes. So the probability that you will win is 14 divided by the chance for every one, 36. So it is 7 over 18. Your chance to win is 7 over 18. Okay, what it means here, does it mean that you will win or not? The concept, as a concept, when you say that the probability to win is 7 over 18, what is the conceptual meaning of that? If you play the game only once, okay, we say that the probability that you will win the game is 7 over 18. Yes, if you played only once, but actually the result will be will appear after you play. Once you play, then you are either loser or winner. Okay. The concept here, it means that if you play the game 18 times, you have high chance to win 7 times. Okay. If you play the same game 18 times, there is a high chance that you will win 7 times. Is it necessary that you will win 7? No, because we have uncertainty here. But it can be, most likely, can be 7, it can be 6, it can be 8. So you are around 7. You are around 7. Is it possible that I win 0 out of 18? If you have, in this case, you are very bad luck. Yes. Okay. Very, very bad luck, because the probability that you win like 0 out of 18 is very low probability. It's like 0.00001. Okay. Is it possible that you will win 18 times out of 18? Also, the probability is very, very small. The highest probability that you will win around, let's say, from 5, okay, to 9 times. This is the most likely. Okay. Now, after we put this simple math, you can yourself quantify your chance to win. Okay. As you repeat this game more, for example, what happens if you repeat the game 180 times? Then you will be very close to win 70 times. If you repeat the game 1,800 times, then you will be very, very close to be 700. As you increase the number of playing the game, you will approach closer and closer to this number. Okay. The random, the sample space, not necessarily to be discrete, like the coins or the die or something. It can be also continuous. For example, the age of a computer before it like damage. It can be, for example, from 0 until infinity, for example. Because we don't have strict number. Infinity here means undefined. Undefined. We have some computers, maybe in some places, they have been now like 30 years or 40 years, they are still working. So we don't know when the computer, for sure that it will damage. So in that case, this is the lifetime of a computer. And then the event of the computer lasts between 4 to 8 years, can be something like that. So between 4 and 8, how many numbers we have? Infinity numbers. So because this is continuous now, not discrete. Not discrete. Because it can be 4 years, it can be 4 years and 1 second, it can be 4 years and 1 microsecond. So you have infinity number that you can put from 4 to 8. Okay. Now we come to one of the most important theories in probability. And because based on this conditional probability, we will have also the Bayesian theorem, where most of machine learning or many machine learning algorithms based on it. So, okay. What is the conditional probability? Usually in our life, events are correlated to each other. Events are correlated. We are not independent. So many things are dependent on the others, and some dependency or the nature of this dependency can be very, very complicated. And so many times we don't know this relation. For example, in the health record for some people, that the relation between diabetic, this person to be diabetic, and then some factors. The factors, for example, the age, his diet like habits, the body mass index (BMI), and for example, his income, for example, wealth, and many factors. Then we can find some relation between, or we can build some model between being the chance to get diabetes and those parameters. But actually, those parameters themselves, they are related to each other. For example, what is the relation between BMI, the body mass index, and, for example, the age? They are not uncorrelated or independent. They are dependent themselves. So in many cases that we assume they are independent, so we take those inputs as independent inputs, but they are dependent somehow. How they are depending, it can be very difficult to know, because some people, for example, they have all the risk factors of get diabetes, but they will not get it until they die, like age 100, very fat, they use very bad diet, but they never get any diabetes. Some people, they are according to the rules that they shouldn't get, but they got it. So how can we build some more accurate model about it? So now we need this conditional probability in order to understand things, how things are, and how things are built, and how can we build more accurate models. So as you can see in these two lectures, that I will try to explain concepts more than math. Of course, we are explaining based on math algorithms or math equations, but we try to go like more about the concepts about these equations. Here what it means that what is the probability in general, just in abstract way, what is the probability that event B will occur given that event A, another event A has already occurred. Okay? So this is the conditional probability. What is the probability that event B will occur? Now, the experiment has not been done yet. So, and now I like to measure my uncertainty, to quantify the uncertainty of event B will happen or not. But I have information. This information says that event A, another event A has already done or occurred. Okay, this was given with this probability equation that this will be the probability of A and B, that the probability that A and B will occur together. Okay, divided by the probability of A. Probability of A, it means that what is the probability that event A will occur regardless of B. A itself, what is the probability that A will occur regardless of B? So now this is the equation. How to prove it? I will not go to the math or to prove this equation, but this equation is very important. However, we can explain it over Venn diagram. So if we have, this is event A and this is event B. Okay, so the probability that, what is the probability that B will occur given that A has occurred? If the probability that B occurred, it means that this area has occurred already because A has occurred. So this area has occurred, divided by the total area of A. Somehow it can describe this the concept. But here this concept is very important. Now I am going to explain a little bit more about this concept. So probability of B given A equal to probability of A and B divided by probability of A. Okay? If A and B are independent, if A and B are independent, so probability of B given A equal to what? If B doesn't care, A has occurred or not, it is independent. So what will be the result? What is the probability of B given A? Who can guess? If A and B are independent to each other, independent. So here A and B, independent.
They are not related at all.
Not related at all. Okay. What will be the result? What do you think? The probability of A, B. What is the chance that B will occur? And you are informed that A has occurred, but now you know that A and B are independent.
Zero.
You said 0. Okay. Who agree that is 0? Okay. Now, if we say that it is 0, if we say that it is 0, okay? What it means 0 here? Means that if A has occurred, B will never occur. So they are dependent.
Okay.
Yeah? If A has occurred, B will never occur. This means that they are dependent. Actually, this is the mutual exclusive. They are, in this case, mutually exclusive. This case is not independent, the independency condition, but this is for the mutual exclusive, that if one has happened, the other never be happy. So, but this is not the case. Another suggestion?
What's the question again? Can you ask the question?
Yeah. Here, what is the probability of B if A has happened, but A and B are independent? So B doesn't care if A happened or not. So what do you think that this probability should be?
50%?
B.
B. Yes. Yes. It will be. It should be probability of B, because it doesn't matter if A has happened or not. So the probability of B given A, if A has happened or not happened, this will not affect it. So the probability of B given A is the same as the probability of B itself. So this is the condition for independence as it is given here. Okay. So if you substitute this here, okay, what we get for independent situation, that probability of B equal to probability of A and B divided by probability of A, and this means that probability of A and B equal to probability of A times probability of B. But this is correct if and only if A and B are independent. A and B are independent. So probability of A and B equal to probability of A times probability of B if event A and event B are independent to each other. Okay? And now we come to the first, as you mentioned, that probability of B given A equal to 0 in case that A and B are mutually exclusive or disjointed events. So it means that if A has happened, B will never happen. Like throwing a coin with head and tail. If you get head, you will never get tail in the same time. It is impossible. So in that case, they are mutually exclusive. Okay? Mutually exclusive events cannot happen in the same time. This is one of the basics in logic, actually, and also in common sense as well. Okay, and what else? Okay, now there's another important equation we can derive from this one. What is probability of A given B? Not B given A, but A given B. It will be the same structure, like probability of A and B, but here will be divided by probability of B because we just changed the location. B instead of A. Okay? Now if you find what is probability of A and B based on this equation, probability of A and B, this equal to probability of A given B times probability of B. Okay. We can substitute this here. Okay. Then we got this probability B given A is equal to probability of A given B times probability of B divided by probability of A. Actually, this is the Bayesian algorithm. This is one of the most important algorithms applied. This is, of course, the basic form. We have more general forms, but this is the most important algorithm that used in estimation theory and in machine learning in many algorithms. That the probability of event B to happen if A has happened, it can be reflected as the probability of A if B has happened, probability of B divided by probability of A. We will see some simple examples to see how much this simple equation has simplified complicated problems to be solved. Because, okay, let me, before I go further, because I like always to connect this to machine learning. So I'm trying now to connect this one to machine learning. So if you have data, like for example x1 and x2, then you have, let's say, some classes that you see, for example, diabetic or non-diabetic, or this machine is faulty or good or whatever. Okay, so we have like class C1 and C2 and C1 and C2. So we have two classes and we have some inputs here. Some inputs gives us the classes. Okay, so we have this record. This is very important. Now I'm trying to connect this equation to machine learning. So now you have, let's say, 1,000 record. Previous record, historical record about certain machine, how it works based on some parameters. It can be more than 2, of course. And based on this, now you have our machine has. We want automatically to see that if we have new record x1 and x2 new record, we like to decide, is it C1 or C2? We like to decide, is it C1 or C2, based on this new record. Okay. Now, what we are looking for, what is the probability that you have C1 based on what? Based on x1, x2, that the attributes that you have, the new attributes. If the probability that of being belong to C1 is larger than the probability of being with C2, then we decide what? We decide C1. Because now we have uncertainty. We are uncertain. Is it class 1 or class 2? But we compute the probability. If the probability of being C1, let's say it was 0.8, and this probability 0.2. Which one you select usually? If the risk is the same, you will take class 1. Okay. Now, how can we compute this one? This one can be computed based on this Bayesian equation, because this one now is the same as B, probability of being in x1, x2 until xm, for example, the attributes given C1 times probability of C1 divided by the probability of being x1, x2 until xn. Okay. From where I can get this information? From the table. Because in the table, I will check, for example, when we have the same attributes, for example, here I have the same attributes. It is C1, I count here. We have 1 here. And here we have again C1. We count, we have 2, we have 3, we have 4. Then, for example, out of 1,000, I found 100 cases where we have probability of x1 until xn divided by, or given that C1. Because given, what means given? I look here to the result. This is C1, C1, C1. I count all of them. Okay? Now I found 100. How many in this table we have? Maybe we have 1,000. Then the probability is 0.1. Then now I compute this probability. This probability is 0.1. Okay. What is BC1? Probability of C1 is the probability that you have a class 1 regardless of the attributes. Then I start just counting. 1, 2, 3, 4, regardless of the attributes. For example, I found 200. Then the probability is 200 divided by 1,000. Then I have here 1 over 5. Then I have here 0.2. Then what is this probability? The probability here, I count how many number I have the same attributes regardless of the class. It is very easy actually. When you build it with your computer, you can do it with very few lines. You can build, this is called Bayesian classifier. This is called Bayesian classifier. So the concept is extremely easy. I mean, but you need to know those basic concepts of probability. As I said that in these 2 lectures, we are not going to cover the whole topics. Actually, many people, they are working in machine learning, like some of them, they are developers or they are like working with codes, and they feel the need for probability and stochastic process, and then they come to have like some basic book in probability theory, designed for undergraduate, and it can be very boring because it takes long time to understand everything related to probability. But in these 2 lectures, we will try to concentrate to the most important things related to our machine learning. Of course, we will come again and again and again to this. So even if you don't understand very well, don't worry, because we will come again for this one. Okay? So those are the concepts that we have explained right now. Okay, let us have a stop here, and we have 15 minutes break, and after 15 minutes it will be 1:30. So the quiz will be activated in your model. So you can take 15 minutes now break, and then you come to the model directly. And maybe we stop here actually. We continue then. Maybe next lecture is Monday. Yes, on Monday we continue. Thank you.